This video is an expansion of the first video I made on the size of the cluster, so if you haven't seen the first video where I performed the calculations to figure out the cluster's approximate size, I suggest you watch that video before you continue with this one. If you don't have time for that, one of the main implications was that you can't think of the cluster as if it was a gemstone on a gem's physical body, because the cluster would end up far too small. So in this follow-up, I'm going to be addressing some common replies I've seen. I'll reiterate some things about fusion, elaborate on gem monster and gem mutant size, and then I'll discuss the topic of using volume rather than linear size. Afterwards, just for fun, I'll show how big some specific gems would be if we swapped their gemstones out with the cluster. I discussed regular fusion in my last video, and I said that if the cluster was to form in such a manner, there are too many unknowns and too much variability to make an accurate size estimation. Also, the cluster prototypes, which are forced fusions of shards rather than willing fusions of physical bodies, do not form in the same manner that regular fusions do. It is possible the cluster takes form differently from the gem mutants, but we simply lack the ability to make decent inferences backed by evidence about how the process would happen. This was discussed in the last video, but I just wanted to drive that point home. People have brought up gem monster and gem mutant sizes, but these don't change the situation all that much. In my calculation, I compared the cluster to a 1-inch spherical gemstone on a 6-foot tall gem. That's a ratio of 1:72 in terms of height. If the cluster was this gem's gemstone, the gem would be 15.5 miles tall. The largest monster body to gemstone size we've seen would be centipedal in the first episode of this show. Ignoring the pinchers on the last segment, its length is about 70 times the gemstone's diameter. The relative gemstone size fluctuates quite a bit in this episode, however, so we can use this shot right here where it's about the smallest to just the ratio. In this shot we can fit 7 gemstones until the jaws tip, while here we can fit about 14, so let's just extrapolate that out to the whole body to get a final ratio of 1 to 140. So if you were to pretend the cluster was the centipedal's gemstone, centipedal would be 30 miles long. That's almost twice as long as the height I had before, but this body is more stretched out, and it's still way smaller than the Earth. Gem mutant size is mostly the same story. It's easy to calculate this with one of the prototypes we saw in the hospital. We can take the shards that make up the amalgam gemstone and stack them, and I even overlap them to count for potential perspective, and it takes 32 to match the height of the mutant. The ratio of gemstone to body size is 1 to 32 in this case, which would obviously just make the formed cluster even smaller. We can do a similar comparison for the hand mutant. We can take its amalgam gemstone and find out how many would stack onto most of its palm, about 7, and then compare this segment to its full body to get a ratio. Since this is a wacky shape though, let's actually reduce the size of this amalgam gemstone to make it a hypothetical sphere, in which case we get about 12. Then we can compare the palm to the rest of the body to estimate a rough ratio, which including the finger arms and the total length, ends up being about 1 to 76. That's only slightly bigger than the ratio I used originally. I would love to see a cluster prototype composed of even more gemstones in the future, say about 10 or 20, to see if the ratio continues to decrease, or if the gems at that point would begin to enlarge like they do in regular fusions. Seeing other large protoclusters would help in making hypotheses about the formed cluster immensely. And now, it's time for geometry. A lot of people thought I should use the volume rather than the linear size to estimate how big the formed cluster would be if it replaced a gemstone on a gem's body. If you do this calculation correctly, it doesn't really change much, even when assuming the cluster is a solid ball with no empty space inside it. For funsies, let's just go through it. Let's use my original values. The cluster is going to be proportionate to a 1-inch gemstone on a 6-foot tall gem. A sphere with a 1-inch diameter has the following volume. The cluster with a diameter of 13,680 inches has the following volume. We can figure out how many 1-inch spherical gemstones would fit into the cluster by dividing, and we get this giant number. This is how many of my hypothetical gemstones it would take to fill out the volume of the cluster. Now, I've seen quite a few people making the mistake of thinking you can just multiply by the height of a gem's body at this point to get a size estimate. No, you cannot do that. That's a massive geometric error. Why is that? Because you'd be jumping from a calculation that was using an exponential relationship into a linear calculation. Let me show you to make this clear. We can say a cube with 3 meter sides is 3 times bigger than a cube with 1 meter sides. The difference in volume, however, is 27. The volume of a cube that is 10 meters, or 10 times bigger, would be 1,000 times that of a 1 meter cube. If you were to multiply the number of gemstones that could fit into the cluster by gem's height to figure out the cluster's height, it would be like multiplying the amount of smaller cubes that could fit into this larger cube to figure out the larger cube's height. You're doing it wrong. It doesn't work. Geometry. What we can do though is pick a volume for the hypothetical gem's body and multiply this by the amount of gemstones that would fit into the cluster to figure out the volume of the cluster's hypothetical physical body. An average adult human has a volume of around 2.4 cubic feet, but let's just increase this to 5 cubic feet. This would be a super beefy body. A 6-foot tall person would be weighing around 300 pounds or so. The volume of the cluster ends up being this many cubic feet, which is nearly 87 cubic miles. This is where I see another common mistake in calculations, forgetting to convert cubic units. You can't just multiply or divide by the typical value, you have to do it by that value cubed, or in other words, to the third power. So a cubic mile is actually almost 150 billion cubic feet. Geometric conversions. So now that I'm finally done discussing all the mistakes, let's get back to the cluster. What we got is 87 cubic miles. Volume is hard to visualize as it is, and it only gets harder with bigger numbers, so let's turn this into a cube and visualize it that way. Cube rooting this value gives us a cube with sides that are 4.43 miles long. So this is how big the cluster would be if it was perfectly crammed into a cube. It's not anywhere near approaching the size of the Earth, and it is within the general ballpark of my linear estimate from last video. It's not off by magnitudes or anything, it's actually a bit smaller. However, this volumetric calculation is more annoying to do, is harder to follow along with, I probably lost a bunch of non-math people along the way, and since the end value isn't all that different anyway, you can all now see why it's so much simpler to just do it with the linear calculations. So after what I can only assume gave some people a major headache, let's have some fun. Let's swap out the gemstones of a few characters with a cluster and figure out how tall that character would be using simple linear scaling. My narration is no longer needed for this portion of the video, so farewell.